US. Should I major in math or physics? Personally, I'd go with physics. LeBron is the GOAT. Yeah, that's probably true. I agree with that. What's your favorite subtopic in particle physics? I do quantum chromodynamics, so I study the strong nuclear force. That's like the best part. If you're new here, make sure you hit that follow button, smash that screen, keep tapping so we can get more people in here so they can ask great questions. Can anyone learn math? Yeah, I think anyone is capable of learning math to any extent. It's just the amount of time it takes for people differ. So, I might learn something in 10 minutes. It might take someone else 5 minutes. They learn it faster than me. It might take someone else 20 minutes. They might be a bit slower. But at the end of the day, everyone can reach an understanding. What is a quark? A quark is a subatomic particle. If you open up a proton, you actually find 3 quarks. And these quarks interact through a new force of nature. It's called the strong nuclear force. They're a lot of fun. I can talk more about them as we go. Where do you live? I was wondering if you studied in Lebanon. Yeah, I did actually. I grew up and I studied in Lebanon up until high school, and then I came to the US. So I have sort of a Lebanese high school background. Explain the tunneling process. Sure. So right now, if I want to go through the wall in my room, I can't do that. The reason I can't do that is because the force from the wall is too strong for me to overcome. I don't have enough energy to go through. Now, in quantum mechanics, not having enough energy is not the key or not the final answer as to whether I can go through the wall or not. The question is there a chance, no matter how small, that there's some chance I end up on the other side of the wall? And in quantum mechanics, that answer is yes, there is some chance, and you can compute what that chance is. So that's the tunneling process. You can have a chance of going through a wall if you're a quantum particle. Any proof of dark matter? We have evidence that it exists. We don't know what it is yet. Particle physics versus astrophysics opinions. So I'm a particle physicist, which means clearly I'm biased, but I think astrophysics has the coolest pictures and they study some of the coolest objects in the universe. How did you choose your grad school? It was kind of an easy choice for me because I only got accepted to 2 places, so it's just a matter of picking one over the other. You can't open a quark. Yeah, so quarks, as far as we know, are fundamental particles. There's nothing inside of them, as far as we know. Who knows, maybe in 1,000 years we'll discover that there's actually maybe little tiny loops of strings or something. How do neutrino detectors work? Essentially, you have a large tank of a liquid, and then you have trillions upon trillions upon trillions of neutrinos that go through that detector, and then you hope that one of those neutrinos smacks into a particle, a nucleus, and when a neutrino smacks into a nucleus, then you end up creating a particle that's charged, that goes faster than light in the liquid, and that creates a bunch of radiation, a bunch of light in the shape of a cone that hits your detector. That's called Cherenkov radiation, and then you infer back that perhaps a neutrino has muddled in your detector. How to create an artificial black hole? It's almost impossible with what we have on Earth, so it won't happen anytime soon or maybe ever. Assalamu alaikum wa alaikum assalam. Will the universe reset itself? So there's a possibility that there's a big crunch, which means that as the universe expands, at some point it'll reverse and it'll start to actually go back down and contract. So if the universe turns over and starts contracting, then you might end up with a big crunch, in which case you might have a bounce after a crunch. And so the universe just goes oscillations back and forth. Thanks for joining, everyone. If you're new here, make sure you tap in that screen, hit that follow button. I appreciate all your questions. Are the collisions a collapse of the wave functions? Not really. You can collide things and maintain their wave functions as uncollapsed. The only time we say that they are collapsed is when they hit our detectors and we measure things. So that's when they collapse. So they found the Higgs boson. So what? So, so what to daily life? Not much. But so what to science and knowledge? A lot, right? So now we understand where particles get their masses from. We know why things don't move at the speed of light always. So one thing we know for sure is that if you have no mass, like a photon of light, then you always move at the speed of light. Why is it that we, as humans, can go at any speed that we want? It's because we have mass. And mass is sort of a property that tells you can go at any speed that you want. That's as long as it's slower than the speed of light. How can we do that? It's because some part of it is because of the Higgs boson. And the Higgs is very essential to the fundamental nature of reality. Why do I keep hearing about nuclear fusion? Yeah, I don't know where they're going with it. I mean, we get incremental progress, but as far as I know, it hasn't. There's no like big breakthrough anytime recently. Is there a chance that wave function collapse is not instantaneous? There's been some work on that. As far as I know, I think wave function collapse doesn't violate relativity, although it might be instantaneous. I'd have to double check, but there's some studies that try to measure whether wave function collapse could be faster than light. If it is faster than light, does it violate relativity? Can you send information faster than light through the wave function? I think the jury's still out, but I'd have to double check. All right. How much earning potential is there as a particle physicist? If you're looking to make a lot of money in life, then you probably don't go into physics. That's my answer. I thought the Higgs boson was just theoretical. Is there evidence for it? What is the evidence? So it's actually not just theoretical. It was theoretical back in 1960. We discovered it in 2012, so very recently. If you look up the Large Hadron Collider, there are two big experiments called the ATLAS experiment and the CMS experiment. And both of these experiments measured the Higgs boson decaying into two photons. And you can look up the discovery of the Higgs boson in 2012. It was a huge triumph of science and the Large Hadron Collider. What is a glue ball? Do you know if there's evidence of that already? What does it mean? Yeah, so I work at the Large Hadron Collider, and we have four main experiments. One of these experiments is called the Large Hadron Collider Beauty Experiment. For short, we call it LHCb. And what we found at LHCb is that there's some candidates that we think might be glue balls. They have all the properties of glue balls. They quack like a glue ball. They walk like a glue ball. They talk like a glue ball. The only problem, the reason we don't claim that they are glue balls, is because there are potentially other particles that behave the same way. So sometimes in physics, you have two particles that behave in a very similar way, and it's hard to distinguish between them in the detector. So that's why we don't make these, press releases that we found glue balls. Do you believe that the new physics learned in colliders has reached the limit due to the Planck scale? We're nowhere near the Planck scale, so no, that's not the issue. Thank you, Los Dos X, for the roses. I'm doing a master in microbiome now. I want to go to physics college next. Any advice? I'm 32. If you want to transition into physics, probably the main thing you want to do is make sure your math is solid, because all physics can be learned as long as your math has a strong foundation. Make sure we're tapping that screen. Thank you everyone for joining today. Let's get up to 5K here so that more people can join the live. And if you're interested in these kinds of things, hit that follow button right there. Okay. Thoughts on quantum computing? I think it's very interesting. I think there's a lot of potential there that we just haven't discovered yet. The problem is, of course, the technology is not there yet. So we still need a lot of work. Instead of string theory, what do you think of a bubble theory? Bubble instead of string in different frequency? I'm not sure what you mean. Maybe you're thinking like instead of a one-dimensional loop, you start talking about a two-dimensional surface. And I guess in principle, you can keep going to more and more dimensions. But you shouldn't make your life more complicated than necessary unless you have reason to. So right now, we don't see any reason to go beyond one loop of a string. So no reason to consider anything more complicated than that. How long is a hot pocket supposed to be nuked for? I'm a physics major. I'm very good at calculus, but struggle in physics courses. Do you have any advice? Yeah, so one thing you could do is when you learn the material in class and you think you haven't really grasped it completely, go to YouTube, watch different lectures on the same materials, see if you get it better, or go read the textbook. Get a different perspective. The more perspectives you read, the more perspectives you watch and listen to, the better you'd understand a subject. So that's number one. Number two, make sure you're solving more problems than your homework. So if your homework demands 5 problems, you should do 7. If your homework is 2 homework sets a week, maybe on the weekend, do 1 extra or 2 extra problems. Go to office hours, talk with your colleagues. See, always try to immerse yourself in the physics scene and you'll find yourself getting better and better in physics. What are the main implications of the muon G-2 experiment? So the main implications there would be some sort of new particle or new force, new interaction in nature that modify the spin of a muon. Unfortunately, recently we found that the G-2 measurement is consistent with the G-2 theory. And so that's probably saying that there's nothing new out there, which is not really that exciting. Can you explain the Higgs mechanism and how it explains the origin of mass for elementary particles? So I'm going to be honest, I don't think I can do that in a TikTok. All analogies are bad that I've heard for how the Higgs gives masses to other particles. And I'd also want to know like what your background is, because, you know, if you've taken, let's say, particle physics before, maybe you're an undergraduate, an upper level undergraduate, then what I would say is that the Higgs is responsible for breaking a symmetry. There is a symmetry in the standard model that maintains masslessness for all the particles. And as soon as that symmetry is broken by the Higgs field, because it acquires what's known as an expectation value, a vacuum expectation value, then that breaks the symmetry. And when you break the symmetry, all of a sudden you get particles with masses, you get actually one particle with no mass, which is the photon. So that degree of freedom remains. Do you think the periodic table could be presented differently so the actinides and the lanthanides aren't excluded? I haven't thought too deeply about the structure of the periodic table. I know that, you know, the way it's structured is because of the quantum numbers that ultimately come from quantum mechanics. But sometimes nature is more complicated than just what you can put on a two-dimensional paper, right? So the fact that we separate them out is not due to us not knowing how to do it. It's just the fact that there are quantum numbers that are hard to put together on a two-dimensional sheet into a nice table. That's, I guess, just sometimes what happens. Maybe someone who's a chemist in here knows different ways of presenting the periodic table. Thanks for being in here, everyone. Make sure you're tapping that screen, and let's get to 5K up here, and hit that follow button if you haven't followed yet. Also, think about subscribing if you're interested. You don't have to. Do you believe in God? Yes, I do. Are we close to fully operating quantum computer? Not at the level of a person. Thank you, Haj, for the gift. We know that there are quantum computers at the level of 10 atoms, maybe more, or 10 electrons and maybe more, but nothing like as a personal device. How do we detect particles without mass? So a photon is a particle without mass. A photon is also known as light, and your eyes are perfect machines to detect those things. So your eyes detect massless particles all the time. So no problem with that. What laws cannot be broken? Well, if something can be broken, then it's no longer a law. So I guess the question is, can a law ever be broken? No, it's in the name. So what things are laws is probably a more interesting question. What do you think you'll want to write your dissertation on? So I'm actually at the final stages of my PhD, so I already have my dissertation being written up, and it's on quantum chromodynamics. So I analyze collisions like this, and we produce these jets of particles that come out, and my job is to study these jets and try to understand which quark in particular created these jets. Was it an up quark? Was it a down quark? A beauty quark? A charm quark? Which quark initiated this mess, this hadronic shower? So that's what I study. Do you have any thoughts on Terence Howard's periodic table? Yes, I do. It's completely BS. That's as most as I can talk on a live. What's the three-body problem? The three-body problem is the idea that if I have three bodies that are interacting gravitationally, then it's almost impossible to predict how they are going to move around each other, how they're going to orbit each other. And the reason is because if I have three bodies, then I have to keep track always at all times of two forces on an object, and those forces are changing all the time. So it becomes incredibly complicated to predict how these bodies will interact. And so in fact, this ends up being a chaotic system. And these chaotic systems become sort of as a, I guess, a pop culture reference, right? Oh, this is a three-body problem, which we now mean like this is a chaotic system. Ultimately, it goes back to this problem with gravity. By the way, Kwana, if you're in here, I think I saw you say something at some point, but then I lost you. If you want to come up, feel free. Why do you think we can't detect dark matter? Mainly because it's a weakly interacting particle. So just as a reminder, we have four forces in nature: gravity, electromagnetism, weak nuclear force, strong nuclear force. So dark matter most likely just interacts with the weak nuclear force and gravity, which are the weakest of the forces. And so if we want to be able to detect it, then we're going to have very sensitive equipment, very sensitive experiments. And that's why it's very difficult to pin it down. What's the best way to study E&M? Open up Griffith's textbook on electrodynamics. I thought it was a pretty good textbook. And read it. Read it carefully and do the problems. Can energy never be destroyed? If so, where does the energy of the living go when they die? So we're confusing two types of energy here. One is the energy in the physics sense. So in physics, we have two types of energy, kinetic and potential. But then we have sort of a colloquial way of talking about energy, right? Like I have energy in the morning, I can do things, whereas a dead person does not have energy, they can't do anything. And so those two types of energies are different, right? One is physics and one is sort of a colloquial way of talking about energy. So if you want the physics way of answering, you would say that a person's energy is still stored in their cells, they're just not being used. Right? So over time, that energy gets dissipated to whatever organisms would decompose the body and stuff like that. What inspired you to do AMA Lives? I don't know. I've been doing this ever since I had a TikTok a while ago, like, I don't know, 2 years, 3 years ago. And I saw like there was a lot of people going on live, and I thought it was fun, and I said, maybe I can do it. And I went on here, and I thought it was pretty fun. People ask very nice, very interesting questions, and so I just came on here. Do you believe in God? Yeah, I do. Advice for sound guys. Not sure what kind of advice I can offer. Does the photon interact with boson since it have no mass? So the photon is a boson. When we say the word boson, what we mean is a particle that has a spin of an integer, either 0 or 1 or 2, etc. And the photon happens to be a boson, which means that it is responsible for carrying the force between two matter particles. Can you tell me the theory of string theory? So the idea behind string theory is that if you take all matter that exists in nature, perhaps it's not all different kinds of matter, electrons, quarks, neutrinos, there's just so many different kinds of things, right? Maybe they're not different. Maybe they're all kind of the same thing. They're all just one dimensional loop of string. And if I get this string to vibrate in different modes, then I can create these different manifestations of that particle, right? So string theory is sort of an elegant way to unify all these particles that we see in nature into sort of one fundamental object. Do you believe in the graviton? Yeah, I think it probably exists, because if you quantize gravity, there's no way to go. You have to get the graviton out. How do you feel about abiogenesis? I think at some point, maybe not in the near future, but probably in the next couple of 100 years, scientists will put their hands on potentially a key thing that contributed to abiogenesis. But right now, I don't think we have any idea of how that happened. In QCD, if the color charges cancel each other, doesn't this mean that the energy will decrease in the proton? So you're thinking of a proton, and in the case of a proton, we need the color to be white, right? So red plus blue plus green, for example, gives you a no color, neutral color, or a white color. Shouldn't the energy go down? The problem is the strong nuclear force doesn't work the same way as the electromagnetic force. The strong nuclear force actually hates it if two things grow apart, and it has the sharp sort of potential. The potential of quantum chromodynamics is really sharp, right? It hates when two quarks are separated. It wants the quarks to be really close to each other. And if you actually calculate the potential energy that is stored in a proton configuration, so 3 quarks with their gluon bindings and all the other pairs of particles that come up, then actually the mass goes up. So you end up having a lot of mass inside of the proton when the quarks bind together because of that gluon potential energy. What's your favorite flavor of quark, I myself am biased towards beauty quarks because that's what I study mainly. How close is the LHC to finding the next particle? We've been looking for, now it's been 12 years since the Higgs boson, and we haven't found any new particles. So it's not looking good at the moment. But that doesn't mean we're not doing good physics. It doesn't mean that if you don't discover a new particle, that you haven't discovered other things in nature. And in fact, we do that all the time. We measure new things in nature that are not new particles. Favorite physics jokes. A photon walks into a hotel. The hotel says, "Any bags?" The photon says, "No, I'm traveling light." I butchered that joke, but you probably heard it before. How do you explain photon light speed over time and reconcile quantum entanglement? I'm not sure what exactly you mean by that. How do I explain and reconcile quantum entanglement? So photons are massless, they have zero mass, and if you have zero mass, then by relativity, you must go at the speed of light. No questions asked, that's it. That's just the rules of relativity. That's just how the universe is. All right, so entanglement work across time. Well, as long as two things are entangled, then they can stay entangled over time. But that state of entanglement will remain over time until you spoil that entanglement. So, in some sense, yes, they persist through time until disturbed. Do you believe tachyons exist? No, I don't. If we find one, that would be great, but I don't think so. Have you heard about dark oxygen? No, I haven't actually. How probable is beauty quark production in collisions? So, at the LHC, we have really high energies, and if you have really high energies, plus really high luminosity, luminosity just means a lot of collisions per second, then you actually create millions and millions and millions of beauty quarks. So, we create them all the time, so it's no problem. And actually, we're kind of clever at the LHC. What we do is, when we collide things, we don't keep that, right? We collide maybe 50,000 of these every few seconds or something. I don't know the exact number, but we collide a lot of things. And actually, most of those collisions are just tossed out. We throw them away. And you might say, why would you do that? Why would you throw away valuable data from these particle collisions? The reason is because we have become very good at detecting what is an interesting collision and what is the same old collision. Because collisions differ. Each collision is unique, and we know how to tell within split seconds whether a collision is good or not interesting, right? And so what we do is we toss out most of these collisions, and we keep the ones that we know, for example, had a beauty quark or a charm quark or something like that. So we've become very good at doing that at the LHC. Are you smarter than Sheldon Cooper? Probably not. Is there a possibility that someone could get powers? I don't know what kind of power you're thinking of, but the LHC will not give you superpowers. It'll probably actually do the opposite. What are your thoughts on unified field theory? Is it dead? There are some good ideas out there. Most famously, SU5, Grand Unified Theories, SO10, Grand Unified Theories, also known as the, what is it called? The Glasgow, I can't remember at the moment. But basically, there are ideas out there. Now, the problem is these ideas typically predict new particles that exist. We haven't found these new particles. Therefore, probably these ideas aren't real. Does that mean unified field theories aren't real at all? No, you can always cook up a new theory of a grand unified theory, and potentially that is the one that's true. All right, guys, make sure you hit that follow button if you haven't followed yet. If you're enjoying this, tap that screen. Let's get up to 10K. Appreciate all the questions and your curiosity. Can you explain strange matter? Yeah, so as I was saying before, we have 6 kinds of quarks. We have up, down, charm and strange, top and bottom. So 6 flavors of quarks. And if you take a proton, then protons are made up of up and down quarks. And these are the stable sort of quarks. Anything else, anything higher than up and down, typically just decay into up and down quarks. So if I look at this strange quark, which is the one that comes next in terms of mass, then potentially there are some stars out there that are composed of just strange matter, and this strange matter would be composed of strange quarks. And the reason these strange quarks wouldn't decay is because of the configuration that they're in and the quantum state that they're in these stars. And so you would imagine there's some star that's made up of these strange quarks. So that's why they're called strange matter. What is the data gathering process for particle collision? Statistical methods, software LHC uses. Yeah, so there's a lot of interesting graphics online that you can look up for the LHC, but the basic idea is whenever a collision happens like this, the first line is something known as a trigger. A trigger is something that takes a quick snapshot and says, is this interesting or is this something that is not interesting? I've seen this before. Should I keep it or should I not keep it? So that's called a trigger. Now suppose the trigger says, oh wait, this is interesting, let me keep it. This is an interesting event. Maybe there's a Higgs boson hidden in here. Maybe there's a beauty quark hidden in here, okay? That's what the trigger does. Now the trigger saves this event and it sort of gives it to the next line, which is sort of a processing part. The processing part says, okay, I have a bunch of pixels that hit my detector. How do I go from pixels like these to actual particle tracks like those? So you have to do a reconstruction step. I have detector measurements and I have to reconstruct from that what kind of particles existed. So did I have an electron? Is this thing a pion? Is this thing a proton? Is this thing a photon? What are these things, right? So that's a reconstruction step. After you go through all these steps, eventually you get some pretty nice data that comes to someone like me who's a data analyst. So I take the final curated data and I say, okay, now I have a list of particles. Now I do actually physics with them, right? So I can combine particles with their momentum and their positions, and I can see if they have a mass or something like that. So then I do the data analysis. Newton or Einstein, who's the GOAT? Sir Isaac Newton, of course. What is the most misunderstood concept in particle physics? Probably the Higgs mechanism. I don't know, there's a lot of things. I mean, I'm not claiming I understand everything. There's a lot of things I don't understand. What is the significance of surf in Lead, South Dakota? So I think you're referring to the Dune experiment, potentially. They have sort of the far detector, which is at the other... So Dune, I believe, has... at Fermilab, their neutrino beam, and then it's supposed to shoot underground all the way to South Dakota where they have their detectors there. So I think the significance is that that's where the detector, the second detector, is placed for this neutrino experiment. Why is the Laplacian everywhere? I think just because derivatives are common, and once you talk about derivatives in higher dimensions, then the Laplacian is your friend. All right. How do we observe subatomic particles? So let me give you an example of something that we do at the LHC. We have a bunch of strips that are made of silicon, and if an electron passes through these silicon strips, it actually makes them it makes them cause an electrical signal through some wires, and so you can actually track the trajectory of an electron that goes through these silicon strips. So it's very accurate, it's very precise. And so if an electron passes through these silicon strips, you can actually see the track that the electron took. So you can see with your own eyes the path that the electron took. So this is some new technology that we use. Back in the day, what they used to do is they used to get a tank and they fill it with some superheated water, for example, or some other liquid. And then what happens is if you have a subatomic particle that goes through this liquid, then it leaves behind a trace, a track. So you can actually see the trajectory of that particle. And it's pretty cool. So the bottom line is you never actually see like a single subatomic particle by itself, right? You always see its effects in a medium. What branch of physics research are you doing for your PhD? So I'm a particle physicist and I work on quantum chromodynamics, which is the study of quarks and gluons, the strong nuclear force. Do you work at the LHC? Yep, I do. I work on the Large Hadron Collider Beauty Experiment. Thoughts on Sean Carroll's hypothesis about quantum fields interacting with space via wormholes. Is that Sean's idea? I thought that was someone else's idea. Quantum fields interacting with space via wormholes. I thought that was like more Leonard Susskind type ideas. Maybe Sean came up with it. I don't know. But yeah, it's something that's like beyond my pay grade in terms of theory. At that point, I'm just a student learning about whether this is possible or not. What in tarnation is a quark? So a quark is something that makes up a proton and a neutron. And if you get 3 of them, then you make a proton. And if you put 2 of them, then you make a new special kind of particle called a meson. And they're very interesting. They are why you exist. By the way, guys, make sure you tap in that screen. Let's get up to 10K and hit that follow button if you're enjoying these lives. Actually, quarks were some of the very first particles that were created right after the Big Bang. So the Big Bang, you imagine it's hot, dense, there's a lot of energy there. What are the first particles that were there? They were, quarks, gluons, electrons, stuff like that. So quarks are fundamental particles. They are like the basic of reality. Do you ever travel to Batavia, Illinois? Nope, never been there. How do you make a quark? There's quarks everywhere inside of you. There's everywhere, every atom in your body has quarks in it. What differentiates a mathematical physicist from a theoretical physicist? Mathematical physics is mostly interested in proving things in terms of theorems using rigorous mathematics, whereas a theoretical physicist is mostly interested in making up physical theories and trying to work out their consequences and potentially link them to experiments. Whereas a mathematical physicist is interested in proving every step, making things rigorous and stuff like that. Can you harness the effects of Lenz's law? In some sense, yeah, it's more about Faraday's law than Lenz's law, because Lenz's law is mostly about the direction, whereas Faraday's law tells you that you actually get an induced current. And that's how we kind of run our economy. Why is the Z boson important? Because it's mediating the weak nuclear force. And if you think the weak nuclear force is important, then the Z boson is important. So that's why it's important. I think it's important. What's the beef between math and physics community? I don't know if there's actual beef, but it's good to always have some banter between the better field physics and the slightly less field math. What's really our charm and strange quarks? So quarks are particles that can feel the strong nuclear force. So if you're a particle that interacts with electromagnetism and the strong nuclear force and the weak nuclear force and gravity, congrats, you're a quark. And the charm and the strange are basically heavier versions of the up and down. They just have a higher mass. That's it. How do I ask questions? You just type it in the chat and hopefully I see it and answer you. If a particle was created in a collider that was in the island of stability, would we ever know? So creating these heavy nuclei in the island of stability is more the work of something known as a facility for rare isotope beams. So in Michigan State University, they have a facility called FRIB, and their job is to create these really heavy nuclei that potentially go into the island of stability. In particle collisions like this, it's more about destruction rather than building something larger, right? So if you smash at really high energies, chances are you're not going to make something that's a conglomerate of many nuclei. Chances are you're going to rip it apart. So you're not going to make something like that. I'm an Aries. What are my lucky numbers? Sorry, unfortunately, you're talking to the wrong person. I wish I knew. What is quantum field theory? Quantum field theory is the idea that perhaps instead of particles having locations in space and, what's an electron? You say it's a particle here and there. Perhaps instead of particles, there are fields that are everywhere. So there's an electron field, there's a photon field. So now you're talking about extended objects that can have vibrations on them and waves. And once you start talking about fields, then you can put that idea with relativity and you can have quantum field theory. So quantum mechanics plus field theory plus relativity gives you quantum field theory. How much math should a physicist know? It depends on what kind of physicist you are. If you're a theoretical physicist, probably a lot of math. If you're someone like me, I did a math undergrad, so I have a bachelor's in mathematics. That doesn't mean that I use real analysis every day. I don't. But it's good to know. It's always good to know. So basically, if you do a physics degree, then you'll study all the way up to differential equations. That's like the cap. But then you can go above if you want to. How do I decide to major physics or math? Any advice? Always think about what you want to do after. So if you're passionate about both of them, then the chances are if you study physics, you'll also study math. But if you study math, chances are you won't study physics. So I'd always go with physics. Which quantum interpretation do you lean to? I used to be a Copenhagen person. Then slowly I got converted away from it. And now I sort of land on the spontaneous collapse theories, which are the GRW theories. We're almost there. We can get to 10K, right? Thanks, everyone. By the way, hit that follow button right there. And consider subscribing if you're interested in these kinds of lives. Always appreciate you all for your questions. What do you think about the measurement problem? So that's what I was just explaining. I think we don't have a clue about what the right answer is. We know that some interpretations are better than others, perhaps philosophically. Right now, I'm at the GRW camp, so spontaneous collapse theories. Yeah, so it's called the GRW. And basically the idea is the wave function collapses not due to a measurement. It just collapses because there's some chance that it will at any moment. It's called a spontaneous collapse or a stochastic collapse. Oh, we hit 10K. Thanks, everyone. Appreciate it. Can we do 20K? Maybe. We'll see. How good are we? Can you send a quantum particle into a black hole to see what happens to the other particle? That's a good question. Chances are, as soon as one of the particles, so I'm assuming you mean entangled particles, and one of them falls into a black hole. That also goes into something known as the information theory paradox, or the black hole information paradox. And now we're getting into territories that are definitely above my pay grade, because I am neither a general relativity expert, nor am I a quantum gravity expert. So stuff like that, I would refrain from answering. I would ask someone who is more apt to answer those things than me. Can you make a black hole with a particle accelerator? So I will give you a very not exciting answer. The answer is no. You will never see a black hole forming from these things. It's just not possible. What's your favorite particle? The beauty quark, because that's what my PhD is on. Which end of the universe theory do you think will occur? Heat death, big rip, etc. Right now, the data seems to indicate that it will be a big rip, but I find the big crunch to be a very nice idea. So I lean towards big crunch. Is there a reason we can't see aliens due to them born near beginning of the universe and light wouldn't show? So I think what you're trying to say is that the light hasn't reached us yet if they were formed at some early stage or something like that. And the answer is probably not, because we know that in the early stages of the universe, it would have been really difficult to have something like a solar system with a stable planet that's fully formed and something that can eventually sustain life. So the idea that aliens were, formed very early on is probably not true. There's a chance that aliens exist now. They're just very far away, and it's, the universe is huge, so you wouldn't expect to actually see them. P.S. I love you, Dr. Ibrahim. Thank you. Thanks a lot. I'm not a doctor yet, but I hopefully will be one day. But thanks. Appreciate all the questions. Do the unconscious content of dreams exist as potential in the quantum field? So here's just some pieces of advice. If we don't understand something like dreams, and we don't understand something like, the fundamental nature of reality, the quantum field theory, it's not a good idea to put two things we don't understand together, because then, your sentence will sound completely, what should I say, unintelligible, maybe. So that doesn't really mean anything, right? Because what do you mean by quantum mechanics affecting dreams and stuff like that? How does this two-slit experiment work? Yeah, so the double-slit experiment is just the idea that if I send waves through a barrier, then what waves do is that they spread out. So a wave that hits a barrier, hits a slit, hits a door, it always seems to spread out. So what happens if I have two barriers? Then I can get a wave here that spreads out, and I get a wave here that spreads out. And what do we know about waves? Waves interfere with each other. And if two waves are interfering, then they have the potential to add up, constructively interfere, and they have the potential to destructively interfere, in which case they add up to zero. So on some spots on the screen, these two waves will add up together, in which case they will constructively interfere. You will see a bright band of light. And on other parts, they will actually destructively interfere, in which case you will see nothing. And so you get this really cool phenomenon where if I send light through two slits, I can get this very nice pattern of alternating bright and dark fringes. By the way, you don't need quantum mechanics to do the double slit experiment. Anyone who ever tells you that you need quantum mechanics to do the double slit experiment is wrong. Just last week, no, 2 weeks ago, we did the double slit experiment in the class that I was teaching using lasers and slits. Okay, it's completely possible just to do it with waves. You don't need quantum mechanics. The big crunch is where time reverses backwards. Not really, it's when the expansion slows down and then it reverses, and then it starts to go back. Thoughts on Susie? At this point, it's not looking good. Susie is dead. Is a warp drive possible? Theoretically, yeah. Experimentally, yeah. My money's on no. Could there be a state where there was nothing but just pure energy? Do you need a particle? Yeah, it's not clear what we mean by pure energy, right? Like energy always exists in some form. It's a bookkeeping device, right? Kinetic energy. We have a particle that's moving, or maybe potential energy. There's a force between two objects. Energy is always related to something. It's a relational quantity. If you say pure energy, that doesn't really mean much. Physics is dead. There hasn't been anything new discovered in ages. That's because you're probably only looking at particle physics and you're only interested in new particles. If that's your metric, then okay, sure. But other fields of physics are well and alive. Cosmology is doing great. Condensed matter physics is doing great. Neutrino physics is doing great. All areas of physics are doing great. Can you elucidate why Heisenberg uncertainty principle leads to quantum fluctuations? So the uncertainty principle, one way to understand it is that you can't have something that's just standing still. Because if I know that this field, for example, is at zero, it's standing still, it's not doing anything, then I have effectively measured its position infinitely precisely. But the uncertainty principle says you can't do that. You can't have an infinite precision of some value. There always has to be some uncertainty, some fluctuation. So it's sort of built in that you would have some fluctuation of the field because of the uncertainty principle. And these fluctuations in the field, this uncertainty, leads to these sort of fluctuations in quantum fields. So it's just sort of baked into the idea of the uncertainty principle. I'm currently a physics major going into my second year of undergrad. Any advice for me going forward? So if you're trying to get into a PhD program, if you're trying to do research, now's a good time to sharpen up your coding skills, learn Python and C++, and then look for some advisor that will take you on as an undergraduate researcher. It's very important that you have research experience, first of all, just so you know if you want to do research or not. And then second of all, in case you want to go later on to grad school, it's good to have that on your CV. So look into doing research in undergrad. Thanks everyone for being here. Make sure you're tapping that screen and you hit that follow button if you're interested in these kinds of lives. I'll go on for maybe 5 more minutes and then I'll see you next time. In physics terminology, what came first, the chicken or egg? I don't know if I can explain that in physics terminology. Probably gonna ask someone in the biological sciences. Can you give a Hadron Collider explanation for dummies? Yeah, the basic idea is you take two clumps of things, take two chairs and just throw them at each other at really high speeds. And what happens is that these chairs will break apart and we send things flying out in all sorts of directions. Now, what's different between chairs and particles is that if I send two chairs at each other, and they'll just break. Chairs in, chairs out. Nothing interesting. Particles are different. If I send in quantum particles and they collide, you actually get new particles. So it's kind of like colliding two chairs, and all of a sudden you get a couch coming out. So the reason we build these things is because we can collide two chairs together and get a couch, or get a futon, or get something else, something different than a chair. Does quantum entanglement negate speed of light since the particles interact instantaneously? In some sense, yes, there could be superluminal interactions, but those interactions do not violate relativity because one cannot send this information faster than light. So once that process happens, how do I then communicate to someone else that, I measured spin up? I can't. I need to go through the speed of light. So ultimately, you can't get around relativity. What is gravity? Gravity is the curvature of space-time, which ultimately can be thought of as a force that pulls together all objects with mass. So it's an attractive force. How do we visualize higher dimensions? There's a good video on YouTube by Eugene Hutoryansky, and he gives you one way of thinking about higher dimensions geometrically. As a mathematician and a physicist, higher dimensions just mean more numbers that you have to write in your vector. So if I'm dealing with 3 dimensions, then I have 3 numbers, right? X, Y, Z. If I'm dealing with 4 dimensions, then I have X, Y, Z, and maybe W if it's space, or T if it's time, right? It's always just one extra number for every dimension. Do you know what dark matter is yet? No, we don't know yet, unfortunately. How feasible is the transition from math, applied math, and CS into physics? If you're applied math, then probably not that difficult, as long as you have taken Physics 1 and Physics 2, I would think. Can beings theoretically live in said higher spatial dimensions? Well, we don't know if the universe has more than 3 dimensions. I was just giving an example. Our universe seems to only have 3 dimensions, right? Length, width, and height. That's all we see. Anything else is just pure theory. Is the Big Bang Theory, the show, all bullshit? Sorry, BS, with the science? Actually, they hired a physicist to make sure that all the science is correct. And in fact, basically all their science is legit. I want to be a particle physicist too. Awesome. Let me know if you have any questions on that process. Feel free to DM me on becoming a particle physicist. Why do neutrinos oscillate? That's a good question. So the reason neutrinos oscillate is because neutrinos come in 3 different flavors, and they come in 3 different masses. And if these masses don't directly correspond to the flavors, then what could happen is that the mass states start twisting around in the flavor states. So if I have a mass neutrino, let's call it M1, then this M1 neutrino can decide to be an electron neutrino, a muon neutrino, or a tau neutrino, or any combination. So it could be in a superposition of these flavor states. And this second mass state can also be a superposition. So you end up with a mismatch between the flavor of the neutrino and the mass of the neutrino. So you get oscillations between flavors and masses. Hi, I study sterile neutrinos at UCLA. That is awesome. Keep me updated if you find anything. What is your theory on multiple universes? I'm mostly indifferent. I think people tend to give them more evidence than they have. Like right now we have 0 evidence that a multiverse exists, right? But people usually talk about them as if, they have some evidence of existing. Let's see here. Thanks for the follows, everyone. All right, I think that's probably enough. Getting a bit tired here, so thanks again, everyone, for joining. If you enjoy these lives and I didn't get to your question, feel free to DM me your question, and if I have time, I'll get back to you. Hit that follow button so you don't miss out on future lives. I'm trying to become more consistent with this, even though I definitely know I won't be. Yeah, just feel free to hit that follow button so you stay updated on these lines. So I appreciate everyone's curiosity. I appreciate all your questions. I'll see you next time. Have a good one.